Welcome to the towering story of the Hoover Dam, a colossal structure that not only reshaped the American landscape, but also revolutionized how we manage water and power. Nestled between the borders of Arizona and Nevada, this massive dam was built during the Great Depression and stands as a symbol of human resilience and ingenuity. Today, we're diving into how the Hoover Dam has left an indelible mark on America's environmental and economic history. The magnificent Hoover Dam, constructed 80 years ago, still stands strong and serves the U.S. in the fields of irrigation, flood control, and power production. Even during torrential rainfall, you won't see Hoover Dam overflowing, causing destruction. Mr. John Savage's surveying team zeroed in on the Black Canyon Mountains beside the Colorado River. The mountains have a decent height and narrow gaps between them, allowing for huge savings on construction materials. However, many design challenges were still ahead for the project's chief engineer. Let's start with the design of a straight concrete wall of uniform width. The strong water pressure obviously causes the wall to deform and bend. You can observe that due to this bending, the outer fibers become elongated and the inner fibers are compressed. This scenario results in tension on the wall's downstream side and compression on its upstream side. When tensile stress is applied to concrete, it easily develops cracks. Generally, modern buildings use steel bars to overcome this issue, as steel rods can readily carry a large tensile load. Now, if you compare this dam's deformed shape with its original shape, you'll notice that both the upstream and downstream fibers are undergoing a length reduction, which means the whole dam body will be under compressive loading. Concrete can withstand strong compression forces. This is the simple beauty of archdam technology. However, if we put the dam under service, it still has a good chance of toppling due to the water pressure. We can solve this issue by increasing the dam's width gradually toward the base. The approach will lower the dam body's center of gravity. The lower the center of gravity, the higher an object's stability. The design we achieved just now is called a gravity arch dam, and this design can overcome the issues of tensile stress and stability. This increasing width design can also resist shear forces. The water pressure diagram on the dam body is not uniform, but is triangular in shape and increases toward the base. However, since the area of the dam increases toward the base, the shear stress value at every cross-section is nearly identical. The next big challenge Savage faced was the height of the dam. The higher the dam, the greater its water storage capacity. This is obviously an advantage for electricity generation and flood control. But is it possible to construct a dam that is the same height as the mountain walls? First, we need to analyze the maximum flood discharge that can occur during the dam's lifespan, which depends on the regional rainfall data and catchment area. After constructing such a tall dam, even during a torrential river flow, if the dam is not getting filled to its capacity, then it has obviously been over-designed. Moreover, building a taller dam requires significantly more materials, drastically increasing its construction cost. Therefore, Mr. Savage selected a height that was cost-effective, meets the water demand of nearby cities, and also does flood control. The height he chose was 726 feet. The main design part of this dam is now complete. Now for the most interesting part, executing its construction. Being an arch-gravity dam, it needs strong mountain walls to transfer the load. Let's take a cross-section of the mountains. You can see the rocks on the surface are weathered and quite weak. Therefore, the first task during Hoover's construction was to remove all those weathered rocks until only the virgin ones remained. To reach the virgin rocks, the workers drilled holes using jackhammers and blasted them using dynamite. After blasting, acrobatic workmen were sent with ropes to clear loose rock from walls, and the excavated material was transferred away via trucks. This dam should have a strong joint with the sidewalls. For this purpose, they excavated the mountain wall in the shape of an arch, again using dynamite explosion. The dam body takes form from these deep holes, making the mountain wall dam connection really strong. Now, the next big question is how the ground will bear the weight of such a massive dam. When excavating, it is crucial to reach a strong layer of soil called hard strata. To find the hard strata, the workers used power shovels and excavated the river till a depth of a whopping 135 feet. They excavated the river in the same width as the base width of the dam. One detail we didn't mention yet is that before they began all this work, they had to first divert the river flow in another direction. To do so, they constructed temporary coffer dams and diversion tunnels. Now it's time for the concreting. For this, we must first arrange the formwork. which is made up of wood for the concreting. Once the formwork or mold is done, we'll start pouring the concrete. However, the main issue here is that when cement reacts with water, it produces heat. Considering the scale of the project, pouring all the concrete at once will create an enormous store of heat, which will result in material expansion and thermal cracks in the concrete, making the project a failure. Here is a construction innovation to solve this issue. The engineers cleverly divided the entire dam area into a number of blocks, each approximately 50 by 50 feet, and poured concrete into each block mold work one by one. These small quantities of concrete took much less time to cool. In addition, they embedded 2-inch diameter steel pipes into these blocks. The pipes carried cool water, which controlled the temperature in the concrete and set it quickly and easily. Once the concrete hardened, the workers filled these steel pipes with a grout cement slurry. This technique proved so effective that the Hoover Dam hasn't shown any cracks to date. Now let's explore the details of Hoover Dam's biggest application, electricity production. Inside the dam's water body are intake towers with several gates along their height to regulate water flow rates. The intake tower is connected to 500-foot-long penstocks that carry water to the turbines. Mr. Savage designed a U-shaped power plant at the base of the dam downstream. Water from the penstocks turns 17 Francis-type vertical turbines, which rotate a series of electric generators. Each generator produces enough electricity to serve 100,000 people. Later, this water is released through outlets downstream for irrigation purposes. The Hoover Dam irrigates more than 1 million acres of land. Interestingly, the dam also creates one of the largest man-made lakes in the world, Lake Mead. This huge water storage facility helps recharge groundwater, increasing the water level in nearby wells. The next obvious application of Hoover Dam is flood control. In case of a flood or heavy rains, the dam stores water in the reservoir, preventing its flow from threatening downstream lives and structures. To address the potential problem of dam overflow, spillways were constructed on either side of the dam upstream. These spills are located 27 feet below the top of the dam. If water reaches that level, it starts flowing into the spillways. From creating Lake Mead to powering millions of homes, the Hoover Dam is more than just a marvel of engineering. It's a cornerstone of modern America. As we reflect on its monumental impact, it's clear that the Hoover Dam isn't just a part of history. It's a vital piece of our ongoing journey towards innovation and sustainability. Thank you for exploring this incredible icon with us today. Don't forget to like, subscribe, and share this video to help us bring more stories like this to you.